Dr. Kashana. Joey's here.
Good morning, Mom. Good morning, Kay.
Good morning.
Good morning.
Morning, everyone.
Good morning, everyone. So thank you for joining us this beautiful Friday morning. Okay, good morning, everyone. So it's 8 o'clock in the morning. Thank you once again for joining us to our PAASE webinars. So the Philippine American Academy of Science and Engineering is a group of Filipino of scientists and researchers of Filipino descent. And for those of you who are interested to learn more about the organization, I'll talk more about our website at the end of this talk. So today, we will have our webinar. So let me just introduce our speaker for this morning. Our speaker for this morning is a professor of chemical engineering and a university fellow at De La Salle University, Manila. He is also currently the vice chancellor for research and innovation at the same institution. He has more than 400 publications with 8,000 citations and an H index of 48. He has won multiple scientific awards from DOST, CHED, NAST, NRCP, PhilAst, DLSAA, and PAASE, to name a few. His areas of interest include carbon management networks, process systems engineering, process integration, process graphs, life cycle assessment, and input-output modeling. He was also listed in Reuters' hot list of top 1,000 climate scientists around the world. 3 of his articles were listed among the 31 publications featured in the UK IChemE Climate Change Collection. So let us all welcome our speaker for today, Professor Raymond Tan.
Thanks very much, Kay. First of all, I want to thank our host, Dr. Kay Aviso, and our PAASE president, Dr. Giselle Concepcion, for giving me this opportunity to give this brief talk this morning. Now, let me begin by sharing my screen. This lecture, which should be maybe a bit more than half an hour, is just an overview of the work I've been doing in carbon management, but in very broad strokes. Now, we don't want to be here all morning. So the talk is entitled Engineering Terrestrial Carbon Drawdown. And I'll begin with this brief quote from a 1977 paper by Freeman Dyson, which is published in Energy. I read this paper about half a decade ago. And Dyson's visionary work was about a future climate emergency. And he speculated that it should be possible to rapidly draw down carbon dioxide from the atmosphere using massive scale photosynthesis and reforestation to absorb excess CO2 in the future should the need arise. And 44 years later, here we are actually facing the very emergency that he envisioned. My talk is divided into 6 parts as shown, and I'll begin by talking about negative emissions technology or technologies in the context of climate change. Now, it's well understood that climate change is one of the major environmental crises that the world is facing. I think many people, like myself, believe it's the most serious one. It is, for example, the 13th Sustainable Development Goal. And when we speak of climate, there are 2 major concerns. Number 1 is mitigation. How do we slow down the climate change which is already occurring through either managing greenhouse gas emissions or through geoengineering techniques or some combination? The other aspect of climate change is there's already plenty of momentum in the shifts that are occurring. So no matter what we do, there will be changes that will occur in the coming decades, thus requiring adaptation strategies as well. And of course, any climate change research portfolio should have a mix of both of these aspects. Now, let me share with you briefly the highlights of a 2018 IPCC report, which highlighted the need to bring down global greenhouse gas emissions to net zero by about the middle of this century. Now, what does that mean? If you look at this graph over here to the top right of your screen, what you see is throughout human history, what we've had is a continuous growth in greenhouse gas emissions to the tune of approximately 40 billion tons per year at the time of the assessment. And what we need to do is within the span of one human generation to reverse a trend that goes back millennia and really drastically draw this down to zero or near zero by the middle of the century. And this is what we need so that in the ensuing decades, the greenhouse gas levels in the atmosphere will be low enough that we begin to slow down climate change, and it's going to be well below 2 degrees Celsius and preferably closer to 1.5 degrees Celsius on average by the end of the century. Now, what we've also seen recently is a veritable bandwagon of zero emissions commitments by different countries. For example, the entire European Union, the UK has also made commitments, Japan recently, and even the largest emitter of greenhouse gases in the world, China, has made a commitment to draw down to zero by 2060, while the other countries have targeted 2050. This is a promising development. Certainly, it's a bit late, but step one is for there to be top-down political commitment to achieve zero emissions, because that will drive actual on-the-ground activities to reduce the emissions. Now, once the political framework has been set, the next question is, how do you actually engineer the drawdown? It's one thing to commit to having these emissions reductions, but it's a second thing to actually, it's a separate thing rather, to actually engineer the changes that will be needed, not just to cut the emissions by 10, 20, 70%, but all the way down to 100%. And what we're going to need is a new family of technologies for carbon dioxide removal, as it's referred to by the IPCC, that's CDR. Other circles refer to these as negative emissions technologies, or NETs. And negative emissions simply refers to a reversal of the direction of emissions, not into the atmosphere, but from the atmosphere. And it's certainly good to see that the future has begun. This popped up in my news feed just yesterday. This is a photograph of, this is a direct air capture plant in Iceland. And what it does, you can see all these rigs with the fans. It basically uses a physical chemical process to skim carbon dioxide from the atmosphere. And take note, that's about 400 parts per million, so it's very dilute, but you skim the CO2 out of the atmosphere and concentrate it, and the captured CO2 is then deposited in an underground geological reservoir. So certainly the technologies are emerging and are being scaled up. Now, let's take a step back and try to understand the global carbon cycle so that we are able to understand critically what it takes to achieve negative emissions. So this is from the IPCC again, this cartoon from 2013. And what we can do is look at where the imbalances take place. The fundamental problem of climate change is that humans, through our activities, are causing a net transfer of carbon from some ecological compartments. For example, fossil fuel deposits or biomass in forests and ecosystems. And we're transferring the carbon, mostly in the form of carbon dioxide, into the atmosphere. And we're upsetting what was a fairly steady state conditions before civilization came along. So if we're shifting the carbon into the atmosphere, we could examine different ways that are naturally occurring in the carbon cycle that go in the opposite direction. And if we can find a way to enhance and engineer these, then we can offset some of the damage that's already occurring. One of the ways by which we can do this is very low tech. It's biochar application. Biochar is simply carbonized biomass. It's what you would call charcoal if you were making barbecue or grilled fish, but it's actually been used for many years, many decades, as a soil enhancement strategy. So you take the carbonized biomass and you apply it to soil as you would compost or organic fertilizer, and that is meant to enhance, or was traditionally meant as a way to enhance soil quality. What has been realized more recently is that the biochar is stable, relatively non-reactive carbon. So if you do it at a large enough scale, you can actually permanently store the carbon in soil. And if you think back to your basic science classes when you were in primary school, what we learned is that photosynthesis takes carbon dioxide from the atmosphere. That's part of the carbon cycle. So plants actually contain carbon that was originally in the atmosphere. And if you carbonize the biomass of the plants and lock it up in stable form and put it in soil, you've actually achieved a net removal of carbon from the atmospheric compartment, and you put it in soil for where it will stay for at least multiple decades or multiple centuries, depending on how you pyrolyze that biomass. So that's relatively low tech. It can be done even in developing countries, and certainly a viable carbon management strategy. One of the other naturally occurring processes, which we also should have learned about back in general science in grade school, is weathering. Weathering is a naturally occurring reaction between many minerals or rocks with water and with carbon dioxide. The problem with this is that it's geologically slow. And if we can accelerate this, we have a process known as enhanced weathering. And what happens is carbonic acid, which is rainwater with traces of dissolved carbon dioxide, would react with certain minerals such as silicates, and there's an exchange of ions, and the carbon ends up being locked up in bicarbonate form, dissolved in the water runoff. And that eventually, of course, carries it into the ocean, where carbon that was once in the atmosphere then becomes stored, at least for long time scales, in the ocean and in bodies of water. So the question then is, how do we accelerate this from geologically slow to a rate that's meaningful for carbon sequestration purposes? So these are the two techniques that I'll focus on, or at least maybe 75% of my talk will be about that. The key fact is both of these have been estimated to be capable of delivering gigaton scale carbon drawdown potential when deployed worldwide. So up here, we have a picture of biochar. Down here, we have a picture of a very common rock called basalt. It's the same rock that you would mix with cement to make concrete. And you could do this. You could pulverize either of these and apply them on agricultural or even marginal lands and take advantage of an acceleration of natural carbon drawdown processes. Now, both of these are scalable to gigatons per year. And why is that essential? If you recall the IPCC graphic that I showed earlier, we're looking at close to 40 gigatons per year of greenhouse gas emissions. So anything that is not at the gigaton scale would really be a drop in the bucket and would just be more of a token action rather than something that's meaningful. So the threshold that we should be looking at is on a global scale, 1 gigaton per year at least, for it to be worth looking at. That sounds good as a solution, but let's keep in mind that everything comes with a price. And in the case of these techniques, we need to look at the implications for land, water, nutrient and energy footprints that will be incurred when we scale these up. And maybe the trade-offs will not be favorable. For example, it takes a lot of energy to grind up the basalt into the very fine dust that you would need for enhanced weathering. It needs to be about as fine as cornstarch for it to be reactive sufficiently with rainwater and carbon dioxide. And of course, there may be adverse impacts if you put too much biochar or too much basalt or other minerals in soil that may affect soil quality. So that needs to be considered as a constraint And the less you can put per unit area, the trade-off now is the more land area you will need to achieve the carbon drawdown. Now, I want to touch upon alternative pathways, which I've also done work in. So one is ocean alkalinization, which is simply if you were to shift the pH of surface water upwards slightly, then it absorbs carbon dioxide through, that creates a thermodynamic gradient for the absorption of carbon dioxide from the atmosphere. But the mainstream in negative emissions technologies are techniques such as direct air capture, which is simply removing through a physical/chemical process carbon dioxide from the atmosphere. Otherwise, you could remove carbon dioxide from point source emissions, like, for example, if you have bioenergy plants, bioenergy power plants, you could retrofit those with CO2 capture and storage, or BECCS, and you isolate the carbon dioxide so that you can dispose of it. Now, the problem is for both of these technologies, you would need some place to dispose of the carbon dioxide that you removed or prevented from being emitted into the atmosphere. And typically we would look at geological formations that are naturally occurring as points of disposal. For example, a natural gas reservoir, such as the one that we have in to the west of the Philippines, once that's depleted, there's actually a reservoir underground which has been shown to be capable of securely storing a fluid. So once we've depleted the gas, we could use the same reservoir as a CO2 storage site. Okay, so that's an overview of climate change and negative emissions. Now let's shift gears and let's talk briefly about process systems engineering. The problem with decarbonization is that solutions are seldom clear-cut. For example, in 2019, a paper was published by Bastin and colleagues in Science. This created a lot of buzz. They estimated that if you take 1 billion hectares of land all over the planet and reforested that land, you would get about 200 gigatons of carbon drawdown. That sounds good, but there was very quickly, after the publication of this paper, the critics pointed out that they were glossing over some of the disadvantages of reforestation, namely water footprint, land footprint, nutrient footprint. And you can read more about that in these papers, and even in the 1977 Dyson paper, that reforestation is part of the solution, but let's not think that it won't come without a price. But the point really is that even obvious solutions might be complicated to the point of requiring more than just a cursory inspection of the problem. So let's bring in at least a toolbox that we can use. And this is a branch of chemical engineering, which is my main area. This is known in the US and North America as process systems engineering. In Europe, it's known as computer-aided process engineering, or CAPE. And in a nutshell, what we do is we develop modeling frameworks to support engineering decisions. Now, let me explain what a modeling framework is vis-a-vis a model. A modeling framework is a template model for a specific class of problems, as opposed to modeling, in which you take an existing framework or an existing template and you plug in your specific numbers and you solve a specific case based on a pre-existing style of representing a system. So in terms of the scientific value chain, we certainly are a bit higher up when you develop modeling frameworks, as opposed to models that are specific to a locale. These are certainly related, but different things. And developing a generic modeling framework is considered higher up the scientific value chain. Now, my own work in modeling frameworks for decarbonization goes back to a paper which I started writing with my colleague and longtime collaborator, Professor Dominic Fu of the University of Nottingham. We started writing this paper in 2005. It was finally published in Energy in 2007 and has, I think it's fair to say it's taken over my career and his as well. Last year, we had our first book on the subject matter. We've been featured left and right, for example, by the UK Institution of Chemical Engineers for this work and for the dozens of other papers that we've done in this area. Now, our first venture into negative emissions goes back a little bit more than a decade, or a little bit less than a decade, and we looked at how we can integrate BECCS, which is biomass-based power plants equipped with capture technology. So you're actually removing, via photosynthesis, you're removing carbon from the atmosphere, but you don't burn all the biomass in such a way that you release the same carbon back into the atmosphere in a closed loop, but you capture some of it and you store it in the geological reservoir. There's an energy penalty for this, but there is a gain in the carbon balance aspect. So this work was our first venture into negative emissions. It's certainly scaled up since then. And in this perspective paper last year, together with our colleague, Professor Santanu from IIT Bombay, we then wrote about the need to scale these techniques up again to multiple gigatons per year, but to also find a way to use modeling frameworks to navigate the bottlenecks when we scale these up. Do we have enough land? Do we have enough water resources and such to be able to do this, not just at the scale of individual countries, but at the scale of continents, such as, say, the ASEAN region or European Union, and even at the global scale. So now let's zoom in on some of the work I've done. And number one is Biochar, featuring some of the work of my former PhD students who are in the audience now. Some of the work, actually, if you're interested in looking at how biochar fits into the picture, you can read this review paper and this perspective paper, which draws up the roadmap for scaling up biochar so that you can use it as a carbon management strategy. And in a country like the Philippines, for example, where we have plenty of agricultural residue, which is underutilized, this is certainly a pathway that's worth exploring for our carbon management commitments to the international community. For example, in a couple of papers from the previous decade, we demonstrated how you can have a biomass-fired plant. And if you're co-producing with all of the things that you're producing, like electricity or steam, if you can produce biochar as a co-product, and you use that biochar not as fuel, but as a soil amendment strategy, then you get net negative emissions for this hypothetical power plant. And again, we developed a modeling framework where you can even customize or tailor the biochar properties for the particular receiving soil. This is the work done by Dr. Belmonte of UST when she was my PhD student. We've developed different techniques for doing this. These are like supply chain models that engineers use in commercial applications nowadays. So mathematical programming techniques, as outlined in this paper. Pinch analysis techniques, which were originally developed in the 1970s for purposes of energy conservation in oil refineries and industrial chemical plants, have been adopted to different applications, including biochar-based carbon management in this 2018 paper. And again, we've taken process graph models. These are graph theoretic model frameworks that were originally developed for plant design purposes, but we've shown that they can be used for network planning when you're trying to apply biochar to different agricultural plantations. And of course, we have extensions where we've looked at the economics in conjunction with the carbon management benefits. Now, much more recently, in work that actually was done after the pandemic started, we've taken the case of countries like the Philippines or like India, which are highly dependent on coal-fired power plants. And we've shown also that we can combine biochar-based techniques and use co-firing. And that means, let me try to walk you through this very quickly. If you have a coal-fired power plant, you can actually modify it marginally and replace, say, 10% of your coal input with biomass. And what that does, because biomass is inherently carbon neutral, by displacing 10% of your coal input with, let's say, rice straw or bagasse, what you could potentially do is immediately cut out or reduce your emissions by 10%. What we showed further is by combining this with what's known as an indirect co-firing strategy, where one of your products is biochar that you don't burn, but you apply on land, you can actually produce not just a 10% cut in emissions, but you have a multiplier effect because the biochar is capturing some of that carbon dioxide and putting it in the ground. But what you need is a framework to be able to plan this within a geographic context. Like if you were to do this in Luzon or parts of the Philippines, then you need a supply chain planning system. Working with some colleagues in Malaysia, we've looked at applying this to their well-developed palm industry, where again, there's plenty of biomass which is underutilized. We looked at the prospect of taking that biomass, turning it into biochar, returning it to the plantations as a carbon management strategy that can be scaled up in countries like Indonesia, Malaysia, Nigeria, and such, where palm oil is a major commodity. All right, now let's shift gears and look at the other terrestrial carbon management technique that I mentioned, which is enhanced weathering. We wrote about the prospect of using these models for enhanced weathering earlier this year. My co-author, no less than our host, Dr. Kay Aviso. And in fact, there's an interview of me about this topic in this podcast. If you have an hour to spare, you can follow the QR code. But let me go through this much faster than that. As with biochar application, the problem with scaling up enhanced weathering for carbon management is you would be mining the basalt, which looks like this, at different locations. You'd be grinding it down to a very fine dust, same fineness as cornstarch, and you would be transporting this dust to different application sites, which would be plantations, or these could be marginal lands. And that really isn't a trivial task if you're moving megatons or gigatons per year of material from one location to the next. You want to do it in a way that maximizes your benefit within the constraints of your resources. So the first model to do this was developed in 2019 by our research team. We've developed extensions recently. This is an application to the case of Taiwan, which is, I think, the 14th or 15th largest producer of iron and steel in the world. And what we did is we looked at their stockpiles of blast furnace slag. This is a byproduct of iron production, and they had two major sites in Taiwan on the west coast and near the south. And we looked at potential application sites throughout the rest of the island. And our model suggests that just using these two kinds of industrial waste, Taiwan could potentially reduce their carbon emissions by 2 million tons per year. And again, just one kind of industrial waste. Unfortunately, the sequestration cost is a bit prohibitive at this stage. Based on our estimates, it's about $170 per ton using this kind of slag. Whereas typically the benchmark we're looking for is to drive down the cost to about $100 per ton. So we're still well above that benchmark. More recently, we've taken a look at a similar problem, but we've applied different modeling frameworks, including the aforementioned pinch analysis techniques. Again, with colleagues from University of Santo Tomas, we've examined how we can combine the two techniques, biochar and enhanced weathering, and apply the same techniques within the same application sites. So if you're a land-constrained country, like say parts of the Philippines would have land constraints, then you could actually have synergistic effects by applying both techniques at the same locations. Now, even more recently, this is a paper that was accepted just last week, working with colleagues in Malaysia and Taiwan. Mainland China rather. We then looked at different kinds of industrial waste, including steel making and iron making slag, red mud from aluminum production, coal fly ash from power plants. And just superimposing the different networks so that we can apply these different minerals, which you would then grind up into fine dust. And these are all slightly alkaline materials. They would be subject to weathering when stockpiled. So all you need to do is accelerate that weathering process, and you would capture significant amounts of carbon dioxide while putting a dent in your solid waste management problems as well. So this illustrates how we can combine the concept of circular economy, which is all about managing solid waste. There are countries and regions with circular economy legislative frameworks. China, for example, the European Union. Now, there is an emerging concept known as the Drawdown Economy, which is still nascent, still to be established. But the idea now is you can similarly have a business and economic framework for carbon dioxide removal. So we were the first to illustrate that you can actually combine those two concepts and put them in a model and manage both solid waste and greenhouse gas emission problems. Now, let me shift gears and talk about some of the other peripheral work that I've done. In 2018, a paper was published by Davies and co-workers, and they proposed that you can take desalination plants and use an electrolytic process to take the desalination waste brine, which is always returned to the sea. This is simply a concentrated brine solution when you've taken out the fresh water. Now, seawater contains plenty of magnesium chloride, and the Davies process, as we now call it, takes electrolysis and uses that to convert some of your magnesium chloride into magnesium hydroxide, which is slightly alkaline. And their argument was, when you take that waste brine, which is already slightly alkaline, and put it in the ocean, then you enhance the absorptive capacity of seawater to capture carbon dioxide. The problem with the Davies process is it's energy intensive. So you need to look at the trade-off between the energy footprint and its negative carbon footprint. What we showed in a series of papers from last year and this year is that you can take the Davies process and not run it by itself, but integrate it into a renewable energy system as a buffering system when you have imbalances between your energy supply and your energy demand, which is always a problem with renewables. And by doing this, we can make it run more profitably and without the energy penalties that arose originally. Now, some of the other work that we've done at De La Salle University is, I mentioned some of the techniques for CO2 capture requiring geological storage. That means you simply pump the carbon dioxide that you've captured into a reservoir, which should hold it in place over the long term. And we're talking about millennia, because any leakage will simply put to waste the effort that you put in to capture the CO2 in the first place. So the engineering problem here is, if you have a candidate geological reservoir for CO2 storage, as we might have at different parts of the Philippines or the US, as the case may be, how can you deduce from geological data the long-term security and stability of this reservoir? And in a couple of papers that were published in 2019 and 20, we developed machine learning techniques to predict with a fair degree of confidence, based on geological data, whether these reservoirs would be capable of storing CO2 securely in the long term. Much more recently, with, again, my longtime collaborator, Professor Fu, and our PhD student, we've looked at how nets or negative emissions can be part of a larger framework for decarbonization in a country, where you're putting in more renewables or putting in carbon capture and storage. And on top of that, you're putting in negative emissions techniques as part of a portfolio at the country level. So this is still work in progress with a couple of prior publications. And of course, if you have multiple nets that you're considering to deploy in a country or a region, whether it's biochar application or enhanced weathering or something as simple as reforestation on a massive scale, then how do how do you assess the different options and judge which ones should be prioritized and which ones should be lower down the hierarchy? And again, we've had a series of papers on these. And much more recently, hot off the press, if we try to look at the different aspects, it's not just about the technology, because there needs to be an ecosystem, if you will, which would enable these negative emissions technologies to actually be deployed commercially. And by ecosystem, that means there needs to be a business model for it. There needs to be a regulatory framework for it. There needs to be public acceptance of some of these exotic techniques. And we developed a new family of causality or knowledge maps known as the P-graph causality map. And we looked at how this applies to decarbonization using negative emissions technologies in this paper. Okay, I think I'll move on to my conclusions now. When it comes to negative emissions technologies, these are certainly going to be needed on a large scale in the future. And there are plenty of research opportunities to look at not just the technologies themselves, but how they fit into a large system. And if you're a social scientist, the social acceptability aspect definitely is an interesting angle to look at. Legal framework, regulatory issues, the business and economic aspect, certainly. Ultimately, the price has to be paid for by someone. So how do you pay for decarbonization? That's certainly an important research problem to look at. And as I move on towards my conclusion, I just want to draw your attention to the nascent carbon drawdown economy. And this is not just science fiction or speculation by an academic researcher. There are actually startups being put up in different parts of the world. And the idea now is this: if there is a need to have negative emissions technologies, because there's a need to have zero net emissions on a global scale, if we know that there will always be companies and industries that will be emitting carbon dioxide, if the goal is net zero, there will be room for companies whose main business model is to generate carbon credits, which can be sold to the net positive emitters of carbon dioxide. And that creates a drawdown economy, which is, again, going to be a reality in the near future. And there will be a need to engineer these technologies within that business model and that ecosystem of the near future. So in conclusion, just a few points. Negative emissions will be necessary if we are to achieve carbon neutrality by the middle of the decade. Let's remember that's only one human generation from today. To be able to scale up so rapidly all of these negative emissions technologies, which are either at the pilot plant scale or demonstration plant or even laboratory scale, to be able to do it in just 2 or 3 decades is a major challenge. Certainly, modeling frameworks that enable you to scale up these techniques rapidly will be part of the solution. And it's especially important to see how new techniques and new technologies and new industries would plug into a pre-existing background system. If you don't do this with models, you may end up with unintended consequences and adverse side effects. And as a result, that leads to various research opportunities. Our PhD student, supervised mainly by Dr. K, is working on co-integration of multiple negative emissions technologies. My PhD student with Professor Fu at the University of Nottingham is working on co-integration nets with a broader decarbonization portfolio. And there will be opportunities to develop various modeling formulations and frameworks. So that concludes my talk, but I do want to thank all my various collaborators, both current and former students and colleagues from 5 different continents, with the exceptions of Antarctica and Africa, and funding agencies in the Philippines for some parts of the work, mainly through PhD scholarships for various students. Finally, I just want to say I'm glad to be speaking this morning. Certainly the PAASE webinars. Friday webinars have been something to look forward to since the pandemic began. But as we all look forward to the reopening of the planet post-pandemic, please feel free to visit us in 2022 and we can discuss urgent research issues in person. Now, that really concludes my talk. Thanks very much. I would be happy to engage you in a discussion on what I consider to be the most important environmental challenge that the scientific community is facing today. Thanks once again.
Okay, thank you very much for that, Dr. Tan. Okay, we actually already have a question. This one comes from Diana Aga. So biochar sources and preparation can vary widely. Is there an optimum biochar type that will work best for carbon dioxide capture? What are the characteristics of biochar that work best for this particular purpose?
Well, first of all, thanks very much for that question. Thanks for coming to my talk. The two fundamental criteria for biochar, which are important, are number one is stability. So we're looking at different markers for stability, including the fixed carbon content and low volatile matter content, as well as there's some work on atomic ratios that predict for long-term stability of the biochar. Because what we really want is when we put that biochar in the soil, the carbon stays locked up and does not slowly decompose and thus release the carbon back into the atmosphere slowly over the course of multiple decades. So that's the first criterion. We're looking at things like low volatiles, high fixed carbon and such. Now, another key issue of which I don't know if my former student, Dr. Bea, is here in the audience, but we look at some of the risks that are associated with biochar application. And that means that the biochar, depending on how you make it, depending on the feedstock that you use, could contain contaminants that you would not want in excess amounts in your soil. That would include, for example, byproducts that are the result of the pyrolysis process, which would include, for example, dioxins and furans, which are on the surface of the biochar, but that would also include a content which was originally in the feedstock to begin with. So you could have heavy metals that are present, or you could have more innocuous but still problematic salts that are present in the biochar. And if you put too much of it in your soil, then you begin degrading the quality of the soil if it's used for agricultural purposes. So those are the two main issues. And some of the work that we did, again, part of the PhD work of Dr. Belmonte, is that you can actually tune the pyrolysis process if you knew something about the receiving soil. That means that, for example, if you're looking at soil pH and such properties, then you can actually customize the kind of biochar that you're putting into the soil based on both the feedstock that you use as well as the processing conditions. Thanks once again for the question.
Okay, thank you for that. So are there any other questions? Yeah, so Dr. Bea is indeed in the audience. Okay, so maybe I'll ask a question. So essentially, based on the work that you've previously done, what would be the main limitation towards the eventual adoption of large-scale implementation of negative emission technologies?
Coincidentally, this slide actually shows most of what I consider to be the obstacles.
Mm-hmm.
Number one is techno-economic uncertainties. And that means that we don't know for sure the actual scale. We can estimate to within an order of magnitude how much carbon we can capture. But for this to be scaled up so that you can put it within a drawdown economy where companies trade the carbon credits, you need to be able to pin down the actual precise carbon drawdown value, because that's going to be paid for by the companies. So verification is certainly an issue. If I put 1,000 tons of biochar in a particular plantation, and I know that 80% of that biochar is carbon, I would need to know for sure how much of that carbon that I put in is actually captured permanently, because there are going to be leakages. So that's the techno-economic uncertainty part. We would have unintended consequences and ripple effects. And Even I go back, for example, to massive reforestation, which if you don't look closely at the problem, might seem to be a solution which has no adverse side effects. But actually, if you put in the wrong trees in a particular location, you might end up depleting water resources because of the water footprint. If you want the trees to grow at a rapid enough rate, then you're going to need inputs of fertilizers, which creates a nutrient footprint that you're just exporting to some other location. So these are ripple effects that you need to be aware of when you scale these up, especially at the gigaton level. So resource limitations, I've mentioned that. Okay, here's one thing that I can touch on. There are proponents of what's known as coastal enhanced weathering, and this entails essentially grinding down rocks like basalt or minerals like olivine, grinding it down to about as fine as table sugar or beach sand, and actually applying this on coastal areas. And the argument there is the same. Basically, because of the wave action that stirs up the minerals that you apply, and it reacts with both water and dissolved carbon dioxide. And it can be scaled up. There's actually a field test in the Western Atlantic, which is being done on this. If you've been paying attention to what's been happening in the Philippines recently, you know about the infamous Dolomite Beach just next to the US Embassy. That actually demonstrates how, to me, it demonstrates if we were to do coastal enhanced weathering, perhaps between the cultural center of the Philippines all the way to the US Embassy, even though you're trying to draw down carbon by doing this with basalt, for example, you'd end up with gray beach along the seafront. That would probably be met with some public outcry for various public and social acceptance reasons. So very often, there's even a paper recently that the perception of naturalness, if you will, would affect the social acceptability of different carbon drawdown techniques. So for instance, reforestation, I don't think people would complain about that, but if you were talking about enhanced weathering, maybe you'd get some resistance. So, and then the legal framework of whether these are carbon credits, which you could then declare as part of your commitments to the Paris Accord. And again, likewise for business models, it is something that if I were to put up a startup company that generates nothing, that sells nothing but carbon credits, how do I verify this so that I can sell the carbon credits, for example, to an airline company, which inherently is very difficult to decarbonize? So these are the challenges, and that's fertile ground for your imagination to do all kinds of research.
Okay, thanks for that. I think Giselle wants to ask something. Yes, Giselle, please.
Thank you, Kay. And Roman, I have great admiration for your work. And I've always asked you, how would you validate your models? And you are in the process of doing that now. But before I ask you about other applications, because we have great potential to test your models now with Alvin working with Leyte governor and LGUs in the agri space. I'd like to ask about biochar, which Diana started asking about. And I just, again, would like to know what are the other drawbacks of biochar implementation. And I just looked at some of the publications and the comments, and it says here loss of land due to erosion, soil compaction during the application, risk of contamination, removal of crop residues, and reduction in worth life rates. And my initial question was whether you had the biosphere or the flora and fauna considered in your modeling. So I know you're looking for that win-win situation, and I think you're getting close to that. It's carbon neutral, and then we'd like to see how this could actually help agriculture if you fine tune your modeling and your computations. So that's my question on biochar, and I have some other questions on weathering. And I had thought about the dolomite, in Manila Bay as well. So that first, Raymond,
Right.
thank
Thank you,
you.
Giselle, for the question. Well, certainly the validation process of the modeling framework, again, I want to emphasize the difference between a modeling framework, which is a logical shell, which allows you to reason out with a model like this, is different from a working model, which is simply plugging in numbers, case-specific numbers into an existing framework. So when we develop modeling frameworks, validation is mathematical in nature. So basically that means that we don't necessarily prove the optimality of the solutions that arise from the modeling frameworks, but we rely on the pre-existing proofs that this is a special case of what is known to be mathematically optimal. Now, validation, not of the modeling framework, but lower down the value chain, validation of a case-specific model really needs to be done in coordination with people on the ground. And again, I take your point about possible adverse effects on agriculture or ecosystems. And this is where the limits of my expertise come up, because I have learned about the limitations based on what I've read and what I've discussed with colleagues, but certainly some of the aspects that pertain to ecosystems, for example, there's a lot of soil science that comes into play because there's what's known as a priming effect. When you put biochar in soil or put some other contaminant or agent in your soil, like crushed basalt, that changes the chemistry of the soil and it could affect the biology of the soil. That means that the microbes that exist in your soil, which normally would generate background greenhouse gas emissions like methane and nitrous oxide, we don't know for sure, and I don't know for sure based on my own expertise, whether any given soil, when you put biochar, would actually have an increase in methane emissions or a decrease in methane emissions. That's the sort of thing that a soil scientist would know about. What I try to contribute, and with the help of my colleagues and students, is a computing framework. So somebody who's a soil scientist who doesn't know that aspect of bird's eye view of the system would be able to plug in his or her expertise into a modeling framework and thus, in effect, be able to combine their expertise with our expertise. And it would be good to, the way I see it, I'm a specialist in this area. I would be happy to share what I know and what I've been discovering with colleagues, but not just in the Philippines. I've made it a point to tell my colleagues and my students, climate change is a global issue. There are no national boundaries in the atmosphere. And I would be just as happy to see carbon dioxide emissions in China or in Malaysia or in the US being reduced, just as happy to see it there as to see it in the Philippines. Because in the end, every ton of carbon that you remove, it all gets mixed up in the atmosphere, and really the Philippines and everyone benefits from every increment of carbon removal. So that's my outlook on this, and I try to just produce solid work. Let me show you something though. Actually, let me bring this up again, and through my frequent conversations with our colleague and former PAASE president, Alice Africa, this caught my eye when I read this. And maybe, I don't know, when I go on sabbatical, maybe I'll explore how to turn the expertise into money. Maybe.
That's great, Raymond. But that's precisely why we are PAASE. So in your audience now, you have many bioscientists. You have many in DLSU. But in PAASE, we have them from other universities. So I would encourage you strongly to organize a chat, okay? And invite all those who attended your talk today and might have an interest in your models and put in the bio data or the considerations. So if there's no one else who has a question,
I think Dr. Pernia has a
oh,
question.
there, Ernie, yes.
Yeah, kindly unmute, Dr. Pernia. All right.
Good morning, everyone. Thank you. Thank you, Raymond.
Ernie, excuse me, you have two connections. That's why they're, interfering.
There's some
I-
feedback. Okay.
Because
Uh-oh.
I was moving
Yes.
around. Now I'm steady. Anyway, good morning, Raymond. Dr. Raymond, thank you for the presentation. It's quite enlightening. I have a laymanish question, and this has to do with I think the model that you were presenting is a major action that countries can do, really bring down the CO2 emissions and to reduce climate by a significant amount. But then I think for ordinary laymen, businessmen, and others, all they can do is really use alternate renewable energy rather than get into directly drawing down carbon. For example, putting solar systems in solar rooftop systems on buildings in Metro Manila. If you ADB, I think is the only major establishment that has been using solar power on its building, and it satisfies its daytime requirements. And I'm not surprised why the other buildings in Makati, in Manila, in Ortigas, they are not putting up rooftop solar panels also, because that's going to contribute to reducing carbon emissions, right? And not only solar but also wind energy, and biomass. You mentioned biomass, of course, that's important too. And so I think even President Biden, U.S. President Biden has mentioned that we have to use more of this renewable energy to make it as much as 40% of electricity consumption by electricity demand by 2040, I think, or 2030, something like that. So you did. I just want to mention that because you didn't mention anything about renewable energy that ordinary people, laymen, businessmen can do to contribute to reducing global warming. So thank you. Just a simple.
Thank you for that, Dr. Pernia. I'll try to make my response as quick as possible, given our time constraints. But certainly renewables are part of the decarbonization portfolio. And if, like the Philippines, if we don't have a net zero commitment, then they should be high priority in the decarbonization strategy of the country. I was concerned more in the long run with the need for many countries to achieve net zero emissions. And that means that renewables alone, if you aim for net zero emissions, would not be sufficient. So why is this the case? Let me illustrate with a very specific class of companies. Airlines have a very limited range of options to decarbonize. And the reason for that is we're not going to see electric airplanes anytime in the near future. So the only real option for decarbonizing, let's say Cebu Pacific or Philippine Airlines, hypothetically, is if they can use biomass-based aviation fuel, which is in very limited supply. I have a paper from several years ago. We estimate the global potential to be just, I think, roughly about 1/5 if you take all the biomass of the planet. So because that's very limited, what I envision as the drawdown economies, companies that really cannot be decarbonized inherently through their operations, will eventually have to buy carbon credits to offset their emissions. And rather than doing it themselves, when you have a drawdown economy, what that means is you outsource the generation of the carbon drawdowns. The Securities and Exchange Commission now requires publicly listed companies to have sustainability reports. So that begins to create that driving force for, at least for publicly listed companies, to look at that. And eventually I foresee maybe there'll be companies in the Philippines that, number one, generate the emissions or generate the negative emissions that you can then sell to companies willing to buy the credits, because it would be economically more efficient for them, cheaper for them to outsource the decarbonization rather than to do it themselves. So that's one aspect of it. But then that creates further market for other companies who maybe will sell their services of verifying carbon credits that are being traded. So then I think the business side of it is, we can imagine this kind of drawdown economy is emerging because there is a need, there's a demand, and eventually there'll be a supply to meet that demand. And I do hope that happens sooner rather than later.
Thanks for that.
And again, thank you for the question.
Okay. I think Giselle has another question, and then I have a couple more in the chat box. So I'll take the chat box after Giselle. Yes, Giselle, please. Yeah, Giselle, kindly unmute.
I'd rather that you let the others' questions be asked first.
All right. Okay, thanks. All right. So there are a couple of questions from Julius. So the first one is, what could be an interesting model or strategy for technically relevant biochar technologies to be deployable in a community level in the Philippine setting? And he has a follow-up question. Are there already safety standards and mechanisms for biochar processing and use either in the Philippines or globally?
Okay, thanks for that question. I think as far as modeling is concerned, we have top-down estimates of biomass availability in the Philippines, which you can deduce very easily from crop statistics. I think what needs to be done, and a good model which should be developed for deployment, would be supply chain level models. Just like when you shop online, there's actually a computer model that determines which branch of this restaurant delivers your food for today. That sort of model would have to be done, because the biomass which would be turned into biochar would be located at different places and would be applied eventually at different locations. So there needs to be some kind of real-time matching of the biomass sources. Where do you put the plants that make the biochar to begin with? And then eventually you ship the product and you put it in the soil. So those things need to be decided on. Now, in terms of, you're right about the regulatory framework, because it is essential that we veer away from what I'd call the cottage industry model of biochar production. Now, the reason for that is, if you don't optimize the engineering of the biochar production, you could end up with product which is contaminated with various undesirable organic or inorganic contaminants, which you would then be putting in the soil. So what we need to do is stay away from the model of just doing backyard style charcoal production, but think of how you can industrialize this to the point where you have strict quality control systems in place. And even then, we would need to find the optimal plant size. Do we need large plants or smaller ones which are dispersed near the biomass sources? So for example, you have maybe a cluster of towns within a radius of 5 or 10 kilometers feeding biomass to a centralized plant. But I think the notion of using, especially at the gigaton scale, I would not agree with the notion of using the standard Philippine model for making charcoal as basis for biochar-based carbon sequestration, because there's just no quality control about the properties of the biochar that you would then be putting in soil.
Okay, thanks for that. The next question comes from Dr. Benja. So can you provide us an estimate of the global investment needed to be able to achieve carbon targets via negative emission technologies?
I'm sorry, I don't have a precise estimate, but the typical benchmark that you would see in literature is $100 per ton of carbon dioxide. So the basic argument there is if you can get it to below $100 per ton, then it's worth looking at in the sense that it's within striking distance of a viable carbon market. So companies can begin trading it. And if you're doing research on a topic which seems to give you above $170 per ton, then that's room for further research to drive down the indicative cost before you can begin to explore actually doing it in the real world.
Okay, thanks for that. And then the next one comes from Felino Lansigan. How can governments and or business sectors be enticed to invest and or co-share costs of CDR or NETs? Can some metrics aside from environmental benefits, including return on investments as such, be offered by the scientific community?
Thanks for that question. I think there are different, different environments that can create that driving force. Number one is if there was a carbon tax, hypothetically, on carbon emissions, then that puts a price tag on both the emissions that a company generates. And it also puts a corresponding profit on carbon drawdown that's created. So taxation regime would be one option, but that needs political will to put in place. What has emerged more easily throughout the world is a carbon market, which is peer-to-peer or business-to-business. A company that has made, for example, a corporate commitment to achieve net zero emissions could either do it through their own internal efforts, but if they don't have the comparative advantage to do this, they could just outsource the carbon drawdown to some other firm that specializes in it and does it better, and then actually cut down the cost of doing that. But that necessitates a business environment for this kind of drawdown economy, the buyers and the sellers of carbon credits. And I think there would be a need for companies to verify that what's being sold is actually as promised. And there's actually a recent case in California now of carbon credits for a reforestation program being questioned by another organization as being unverifiable. So I think those are the driving forces. Now, one other aspect of the terrestrial drawdown techniques that I focused on earlier, the biochar application and mineral powder application or rock application, these techniques are actually used on a limited scale already in different parts of the world, but not for carbon sequestration purposes. These are used as soil amendment techniques. So one of the ways to kickstart this is if you begin with the intent of improving agricultural productivity so that the farmers actually benefit directly. And then if you're able to account for the carbon drawdown benefits on top of the agricultural gains, and maybe find a way to finance the gains. For example, if plantation owners can sell the credits to airlines, for example, then that would be a way to stimulate this kind of an economy.
Okay, thanks. So there's a comment from Dr. Rason in the chat. So $100 per ton for 120 gigatons is a lot of money. So yeah, so since you mentioned $100 per ton, so does it mean that this is currently like more or less the price for other types of technologies that are being utilized for carbon sequestration or for reducing carbon?
Well, first of all, special shout out to Louis, who taught me everything I know about reaction engineering a quarter of a century ago. Yeah, that's a lot of money. About the $100 per ton. It's more like a rule of thumb. It's not really pegged on any, it's from the perspective of a carbon market. And you can imagine that anything costing double digits US dollars per ton would be something that is viable within carbon tax or carbon market regime. And anything beyond this might distort the economics too much. I think this is where environmental economists should come into the picture, because there have been efforts, and there are efforts now, to estimate the cost of climate change. And that way, these are what are known by economists as external costs. These are costs not borne by anyone specifically, but are diffuse, and everyone bears a bit of that cost. And there are different ways to estimate this. I'm not an economist myself, but I do understand that the $100 per ton is within the same order of magnitude as many estimates for the damage incurred from emitting 1 ton of carbon dioxide into the atmosphere.
Okay, thanks for that. And then finally, yes, Giselle.
Thanks, Kay. You know, I'm on a side Viber exchange with Toby, who just came in and he's late. And he has a question on biochar, whether it would work in typhoon-ridden areas. Okay, but my own question is more chemical. So there are many chemists and biochemists in the audience, and of course, biologists, including agribiologists. So we're concerned about pyrolysis, which is biochar, the biochar process, versus incineration, which we know has been an issue in our country. And just to get incineration going is tough. Okay, but we'll leave that to regulatory and to government policy and also economists to address, which again tells me it's so important to have a dialogue with us, Raymond and Kay. I hope you can arrange. This is a very important area of research. But anyway, going back to pyrolysis. So that's like oxygen free. Precisely, you want to remove the oxygen, right? So that you can trap the carbon without oxygen in the soil. And we already talked about what the consequences might be on the soil and the microbial flora, as well as macro, flora and fauna. Okay. Now, I'd like to also address enhanced weathering. And you said dolomite might have been moved for this purpose, not just for tourism, but for ecological purposes. No? So I'd like to know the consequences of pulverization and enhanced, weathering of rock and basalt, and what would the specifics be of this? Where would it come from? And what's the consequence on runoff? So in marine science, we know we are always concerned about fine soil or fine rock or whatever that just gets into the water as silt. So in a typhoon-ridden country, what's the chance that you do this and then you move it to soil? And then during typhoons or heavy rainfall, then you have this consequence of having pulverized the soil to trap the carbon dioxide. And you have to do it very finely so that you can increase the surface area to trap or to react with the carbon dioxide. So Raymond, these matters concern us. Okay, can you have just some quick answers? And then I think, okay, we're running out of time, but this is so important. And I hope
I can go on for the rest of the morning. But
yes.
I'm sure.
Yes.
Okay,
so I think, thanks.
Thank you for that. Let me answer backwards. Starting with enhanced weathering. The two options that I mentioned are terrestrial enhanced weathering, in which you take the basalt or rock powder in general, and you apply it to agricultural land. I showed this is actually a practice already being done for pH adjustment of soil. So if your soil is too acidic, it's actually possible to put alkaline pulverized rock to adjust the pH. And the basic chemistry here is that the carbon dioxide, the carbon and silicon atoms switch places. So you would have silicates in the rock to begin with, and carbon dioxide dissolved in water. And eventually they switch places and you end up with silica in place of what was originally CO2. And then bicarbonate ion dissolved in the runoff water. So it's not, these are not in solid form, but you have bicarbonate ions which actually occur in runoff in general. So that's carried eventually by rivers. The runoff goes into rivers and eventually, ultimately in the sea. So that's the big picture cycle that we're looking at. The other way to do it is that you put it in a coastal environment. And this time you don't do it, you don't need to have it at the fineness of cornstarch. You just essentially need to make artificial sand. And I was using dolomite as a way to illustrate how, even if we were to do this for a good purpose, which is carbon sequestration, if you were to turn an entire strip of beach, let's say all the beaches of Boracay might be turned gray if you use basalt, or green if you use olivine, for example, it would turn green. I would put a DLSU flag in the middle of it to say, this is green beach. But the point is, subtle changes like this would not be taken lightly by the public. So there needs to be an understanding of what are the consequences. So in terms of the turbidity, if you're dealing with what is essentially sand in terms of particle size, then it would have no different physical effect as beach sand, which is already there to begin with. Perhaps a more relevant concern or constraint would be localized pH changes. I'm sure that marine scientists would be concerned about the elevation of pH as a result of the slow dissolution of the rocks that you put in. On the other hand, and again, we need environmental chemists to look into this. Maybe that just offsets the acidification which is already taking place because of excess carbon dioxide.
Absolutely. So ocean acidification is major consideration.
But this would cause alkalinization. So
right, exactly.
We know that they go in opposite directions. Yes. We don't know how much the models come into play to figure out how much you need so you don't upset the pH beyond what's safe.
That's why it's a win. It could be a win-win because you would be offsetting or trying to reverse ocean acidification. So I think it's a great potential, but on the other hand, I'm actually concerned also about siltation. Okay, runoff from land to water. Okay. Anyway, this is not chemical oceanography. Is not my area, but there are PAASE members who are specialists in this area. So I think Raymond, that's so great that you are sharing this with us today. Thank you.
Thank you as well for your questions.
Okay, I guess that's all we have for today. It's already 9:17. Thank you so much for that, Dr. Tan, and thank you so much for everyone who asked questions. I do hope that everyone learned something new today. So before we go, I just wanted to share with everyone our website. So we are in paase.org. So this is our website, and we announce all our programs and activities in the website. So if you're interested to know what's going on with PAASE, what would be the next lecture for the week, and sometimes we also have fireside chats with various experts looking at different topics. We also want to invite you for our upcoming meeting, which will be in October. It will be held in the US, but it will be a hybrid seminar. So it will be on October. Okay, I cannot see the date here. Giselle, can you? It's
yes. May I? Yeah, it's yes, October 8 to 11. 8 to 11. So I think you have to look carefully at the program, which is on the website. See there, you have details. So this one now shows announcements. Maybe you can go up to do the left arrow, okay, so that you can show because this is the announcements box.
Okay, so this would be
You have to,
here.
well, the left top
This one.
arrow, you move to the home page of the
Okay.
PAASE website. But while Kay's doing that and showing us the details of the 41st APAMS conference, Kay, I'd also like everyone to know that next Friday,
Mhm.
our fireside chat will have Luli, National Scientist Lourdes Cruz, talk about future Earth in the LGUs. So she's continuously holding future Earth workshops to educate the LGUs. And we know very well that that is so important from the experience of Alvin Glaba in Leyte. Okay, so next week, our main speaker will speak on matters that relate directly to what Raymond talked to us about today. And we will have this event co-hosted with Ino Lansigan. Yes, Ino? And we're hoping that our new member, MD PhD, his name is Ramon Enzo Ginto of Harvard and St. Luke's Medical Center, lead person in One Health or Planetary Health, will be a reactor. And Luli also suggested Doy Romero of Ateneo. Okay, so we're going to have this next Friday, September 17, also at 8 a.m. So Raymond, tuloy-tuloy lang yung discussion about climate change and future Earth. So there you have the there you have it.
Okay, there we go.
Call for
8 to 11. 8
nominations.
to 11.
Yes, yes,
Yeah,
yes.
it will be on October 8 to 11.
8 to 11.
Okay,
Yes.
so
Look at that. So there's online, and then there's, of course, there's also the live conference.
Okay.
All right. Thank you.
okay, I think that's all for us today. Thank you so much, everyone, for participating in this event, and have a nice weekend. Well, enjoy the rest of Friday, and hope to see you in our future events. Thank you, guys.
Thank you. Thanks, everyone. Have a good weekend.
Thank you.
Thank you.
Thank you. Thank you. Bye bye.